Hello, this is our last lecture, the concurrent computing course. And actually, this is the last part in which we discussed two programming languages, Java and Ada, regarding their capability in doing synchronization and concurrency. This is the last one, which is also a short one. We talk about Pthreads. There was a standard called POSIX, Portable Operating System Interfaces. This is a family of standards for maintaining compatibility between operating systems. The POSIX is a Unix-like operating system environment and is currently available on Unix, Windows OS 2, and even DOS, which is a subset of POSIX. Basically, a programmer using POSIX writes his program just like a Unix program. You can fork, you can wait, and so on. In this way, if your program is based on POSIX, and if the system has the POSIX standard installed, then your program is very portable. Pthreads, that is, POSIX threads, is a POSIX standard for threads. The standard POSIX.1c thread extension defines interfaces for thread creation and manipulation and so on. This standard also defines thread management, mutexes, conditions, rewrite, lock, and barriers. Pthread standard does not have semaphores. It only has condition variables and condition weight and signal. There is no monitors either. The condition weight and signal follows the Mesa type rather than the Hoare type. The differences between these two types were discussed in the monitor units. As we mentioned earlier, POSIX and Pthreads are Unix-like and inherits many Unix ideas. One of them, which is used extensively, is the variable error number. This is a variable that provides you with the last error in your program. The variable error number is defined in header error number.h. Therefore, you have to, in order to use error number, you have to include this header file. For an example, E meaning error, invalid means the value specified by the mutex or a condition is invalid. E, again, the maximum number of recursive locks for mutex has been exceeded. Remember, we learned the reentrant lock in Java. You cannot allow a owner keeps locking on the same lock indefinitely. And finally, EBC, it means the mutex cannot be acquired because it was already locked. So there are other possible return values into the error number. So please check the manual for the details. Now, we'll briefly introduce to you some of those important thread-related function calls, just briefly. So when you use pthread, always include pthread.h, this header file. To create a thread, you call Pthread Create. This function had 1, 2, 3, and 4 arguments. The first one is a pointer to a variable TID whose type is pthread_t. That is the ID of the created thread. And ATTR is a pointer to the attribute of a set of attributes to be used in order to create this thread. And this has a type of pthread underbar ATTR underbar T. And finally, when you create a thread, you need to provide it with a function. This function is here, a start. Of course, you don't need to use this name. You can use any function name. And the function here has a void pointer. And the fourth argument is the argument list to be provided to the start function when it starts running. So for most of the time, we just use null here if we just want to use default value. What are the default value? For an example, a thread runs, it must have a stack. Remember in the discussion of thread, a thread must have its own stack rather than sharing the stack of the containing process. So what is the size of this stack? So this is one of the attributes. So you could also use pthread underbar attribute init to initialize this. So the ID of the newly created thread will be returned here. Now, the return value of any pthread function, if it is 0, it means it's okay. Therefore, if pthread underbar create returns 0, it means a thread has been successfully created. Otherwise, pthread create would return -1, just like Unix. When you see a return value being negative, you know something was wrong. The next pthread function to be discussed is Pthread Exit. A thread calls Pthread Exit terminates the calling thread and return the value stored in this location, pointed to by a void pointer status. Now, this is different from thread matter. When a thread exits, the exiting thread could create some return value or exit value here, which could be anything, integer, structure, strings, and so on, as long as everybody knows what the type it is. So the exiting thread saves something here and return a pointer to it. So this value would be known to any joining thread. And if you're not interested in the use of exit value, then just put null here. Now, it's very important to note that pthread exit never returns. The reason is the caller wants to exit. By the time pthread exit is executed, the calling thread has already been killed. Now, quickly go through it. Pthread exit terminates the calling thread and return the value stored in here to any joining thread. That is, if a thread will join with the thread that calls pthread exit, would be able to access this value. The second important thing to know is pthread exit never returns. And finally, if you don't use the exit value, just put null. So how do you access the exit value? That's our next topic, thread join. Pthread join, the caller of Pthread join would wait for the thread to complete, just like we did for thread manager. And then once that thread completes, that is either that thread normally exit or that thread calls Pthread Exit, the exit value will be returned. Now, if you don't use exit value, you just put null here, meaning I don't care. Now, if you have a pointer here, it's actually a double pointer. The status pointer is here. It points to a pointer. That pointer is a void pointer to a place where the exit value is stored. So if join failed, thread join returns -1. So you have to check error number for the reason. Check the manual for the return value. Otherwise, thread join returns 0. So far, this is exactly like what we have done with thread manager, except that the exit value must be stored somewhere. In thread manager, we encourage you not to return anything. If you wish to return anything, put it in as a global entity. And when you save things there, you say mutex lock, so that a critical section would be created. And once anyone wants to retrieve and save the manual, the value, it will be mutually exclusive. Now, the next important topic would be mutex. A mutex in Pthread has a type Pthread mutex T. Always keep in mind, mutexes cannot be copied. So you have to use pointer. Why it cannot be copied? It's very simple. Suppose I create a mutex in order to protect my critical section, and you copy that mutex to your location, then we actually have 2 mutexes. So always use pointer. And this is a macro. This is a macro. Pthread mutex initializer. This is used for initializing a static mutex. If you don't care, then you just use null, which means you use all default import. So if you wish to create a mutex and dynamically initialize it, then call Pthread mutex init to initialize a mutex dynamically. If successful, if the initialization was successful, it returns 0. Otherwise, this init function returns -1. Check error number for the reason of failure. So here, init, Pthread mutex init, you provide a mutex, a pointer to it, and a pointer to its attribute. Here, you want to destroy a mutex. It's pretty easy. You just call Pthread mutex destroy, and that corresponding mutex will be deleted. If this deletion was successful, Pthread mutex destroy returns 0. Otherwise, it returns -1 and set error number value. Now, always remember this. Do not destroy a mutex object while it was locked or referenced by another thread. That is why someone is using a mutex, even though you are the owner, you'd better don't delete it. You delete until no one is using it. Now for the mutex attribute, you could set the type of the mutex to allow recursive locking or reporting deadlock if the owner locks again. Remember in the lecture of Java thread, re-entry lock allows the owner of a lock to lock it again before the lock was unlocked. So this is recursive locking. If you wish a lock to be used as a recursive lock, then you have to initialize it by setting a lock type. Or by default, if you lock it again, definitely you have a deadlock. That's pretty simple. If you lock a lock and then you try to lock it again, of course, the lock is already locked. You are the owner. If you try to lock it again, deadlock, because you have a circular waiting. If the caller successfully acquired the lock, Pthread mutex lock returns 0. That is, use this one to lock the lock. Otherwise, it returns -1, and the caller failed to acquire the mutex. Check the reason here. Now, after using the lock, the caller or the owner of the lock must release it so that other thread could use it. So if the caller successfully released the mutex, Pthread unlocked here returns 0. Otherwise, it returns -1. Why? It would return -1, for example. As we mentioned, when we talk about mutex, only the owner can unlock a lock it owns. Therefore, if I own the lock, and you try to unlock it, you would definitely get a negative return value because you are not owner. So check ERR number for the possible reason. So it's very easy. This one, similar to Pthread Monitor's mutex lock. This one is similar to Pthread Monitor's mutex unlock. Pthread also has a try lock. If Pthread mutex try lock returns 0, the caller successfully acquired the lock and becomes the owner of it. That is a thread called Pthread mutex try lock and gets a return value 0. It means the caller becomes the owner of that lock. And if the return value is -1, the caller failed to acquire the lock. The reason, check error number. For an example, if error number is EBC, that means the lock is already locked. Java's re-entrant lock is supported by the use of Pthread mutex attribute set type to allow recursive locking. But for a beginner, in my experience, please try not to use the try lock. Then the next topic is condition variables. Mind you, Pthread has condition variables, but Pthread has no monitor. If you wish to use monitor, you have to simulate one. We will mention this. So condition variables in Pthread are usually used with a mutex to enforce mutual exclusion. Remember, a monitor has a natural boundary for mutual exclusion. So when you use a condition variable, it means you are in a monitor. And the mutual exclusion of that monitor is simulated by this associated mutex. The type of condition variable is Pthread count T. And Pthread count initializer is a macro for initializing a condition variable statically. A condition variable can also be initialized dynamically using a Pthread condition variable init. So this is a static initialization. So condition in, so we create a condition variable giving a pointer, and this attributes are used to initializers. And you destroy a condition variable by calling Pthread condition destroy. Now, the Pthread condition variable initializer, if you use null for the second argument here, or default attributes are used. And if the init function returns 0, the initialization was successful. Otherwise, the return value is -1, check error number. And if you want to destroy the condition variable, call this function. If it returns 0, the deletion was successful. Otherwise, check ERR number for the reason. So far, it's pretty easy. Now, the messy part is here. Initialization only used once, destroy only used once, but in a condition variable related program, you wait and signal multiple times. In Pthread, we have the following function: condition wait, condition signal, and a condition broadcast. The condition broadcast is similar to Java's notify all. Actually, in the module components of this series of lecture, we discussed broadcast. So please review that module extension unit. You'll see how condition broadcast can be used. So let's look at thread waits. When a thread must wait on condition variable, thus thread must provide the mutex lock it has already acquired earlier to condition wait. So basically, condition wait has two arguments. The first one is a pointer to a condition variable. The second one is a pointer to a mutex. This mutex was acquired by the caller some time ago. In other words, when a thread calls the condition wait, it must be the owner of the associated mutex lock. Once the caller calls the condition wait, just like in Pthread Monitor and our theoretical discussion, it waits immediately. The caller waits immediately, and the mutex it owns is taken away. So in other words, when the caller calls condition wait, it's blocked immediately, no matter what. And the mutex it owns is taken away. So the mutex becomes open. At the same time, the caller of this condition wait would be put into the waiting list of the condition variable until later on, the caller will be removed from this waiting list. At this moment, the mutex becomes open. Which thread can acquire this mutex is not specified. We don't know. So never assume that thread A calls condition wait would release the condition variable and then thread B would get it. Never make this kind of assumption. So because the mutex is used to build a monitor boundary, therefore, for each condition to be used in a simulator in a monitor, it should have only one mutex associated. If condition wait was successful, it returned 0. Otherwise, it returned value gives error condition. Check the ERR/NO for that. So this is wait. Quickly recap. When a thread calls condition wait, must have already acquired the associated mutex. When you call condition wait, not only you need to provide the condition variable, but also the associated mutex. The following steps would be executed in an atomic way. The caller will be put into the waiting list of the condition. The lock is taken away from the owner. That is, the caller is no more, at least for this moment, is not the owner of the mutex. And then the mutex becomes open for anyone who execute a lock to use. Remind you, because the mutex is used to simulate the mutual exclusion boundary of a monitor. So each condition should only be associated with one mutex. Then let's look at condition signal. When a thread calls condition signal, it would release a thread that is waiting on the waiting list of this condition. If there are more than one thread waiting, one is picked. But we don't know which one will be picked. Never assume any order. Otherwise, if there's no one waiting on that condition, this call has no effect, as if it never happened. So as you can see, a thread calls condition signal. The only argument would be the condition variable to be signaled. So if the condition signal returns 0, it means the signal was successful. Otherwise, it returns -1, and please check the error number. For the broadcast, when we call condition broadcast, all thread waiting on this waiting list would be released. So the difference between condition signal and condition broadcast is condition signal only release one. We don't know which one if there are multiple thread waiting. And the broadcast call would release all thread waiting on that condition variable if there are at least one. Now, the remaining is what I said, messy. Please remember this carefully. Otherwise, your Pthread program using condition may be in trouble. So the released thread, so what does that mean by the released thread? The thread was on the waiting list of a condition variable. Now, when someone calls condition signal, a thread is released from the condition. But this thread does not get the mutex back immediately. In other words, the released thread would be joining those threads who are waiting for the mutex. So this is different from a Horde type. This is a Mesa type. The released thread is removed from the waiting list and join the waiting list of thread who are waiting to acquire the mutex. Whether the released thread can get the mutex immediately, we do not know. Then know that the mutex being held by the thread calling condition signal. Okay, why? As we mentioned multiple times, condition variables is associated with a mutex. You have to acquire the mutex before you can call condition wait and condition signal. So if you call condition wait, you lost mutex and wait. If you call condition signal, it means you have already acquired the lock. Otherwise, you cannot call this condition signal. If you call that, the system will know you are not the owner of the mutex associated with corresponding condition. So you fail. So it means when a thread calls condition signal, it has its mutex. Therefore, when the released thread is removed from the condition variables waiting list, it must wait somewhere until the caller to condition signal will release the mutex sometime later. So that means this is a Mesa type. In the whole type, the thread calls condition signal, yield the monitor to the release one immediately. The Mesa type goes as follows. The thread calls condition signal continues its execution. The released one will be released and waits outside of the monitor until the mutex that enforces the monitor boundary would become available later. Isn't Pthreads condition variable simulates Mesa Monitor? Therefore, after the release thread gets the mutex and runs, it must check the condition and perhaps wait again. Why? Suppose thread A waits for variable sum to become non-zero. Now, when thread A checks variable sum, its value was 0. So thread A waits on a condition variable. And then some other thread, say thread B, adding 1 to the variable sum. Then thread B makes the value of sum non-zero. Therefore, thread B uses condition signal to release A, who has been waiting on that condition variable probably for some time. So thread A is removed from condition variable, waiting to get back. Now, thread B now has the mutex. Thread B continues execution and eventually exit the monitor by unlocking the mutex. Now the mutex is open. At least we have one thread waiting to use that mutex. Which one? The release the thread A. But it could be multiple one. In addition to A, there could be thread X, Y, or Z waiting there to use the mutex. What if thread A is not lucky, fail to get the mutex? Instead, thread Y gets the mutex. So thread Y gets into the monitor and messing around. Thread Y could change the value of sum back to 0. So when next time the mutex is open, thread A gets back. What's the problem? The condition thread A was waiting, that is sum being non-zero, is no more there. So this is what I mean. After the release thread gets the mutex back and runs, it must check the condition and perhaps waits again. So all of these steps are done atomically and atomically. That is, a signal happens, a thread is released and put outside of the mutex, and then the caller to the condition variable continues the execution. This is for signal. The same for wait. These sets of activities are done atomically. You don't need to worry about that. And they are done in an atomic way, indivisible, uninterruptible. So this is a complexity of understanding condition variables in Pthread. Now, Pthread condition broadcast released all waiting thread on the condition variable. So Pthread condition broadcast is the same as notify all in Java. After the release thread gets the mutex back and run again, please check the condition and perhaps must wait again. So this is the condition variable discussion. Now, if you feel that you missed something, strongly encourage you to watch the first few lectures of Monitor series. There you learn a lot of conceptual and programming practice. Now, as we mentioned, the condition signal and condition wait follows the Mesa Monitor. Then if you are used to monitor we discussed earlier, then simulating a Mesa Monitor is fairly easy. We use a mutex for protecting the monitor. Lock and unlock this mutex upon entering and exiting the monitor. When a thread calls a condition wait, it relinquishes the monitor mutex. That's automatically done. Once blocked, the monitor mutex becomes available to other thread. If the release thread from a condition variable eventually gets the mutex, recheck the condition, because this is a Mesa type monitor. Now, here's the code. We define a monitor lock initialized by all the default value. We define a condition variable count initialized by all the default values. So this is a monitor procedure. When you call a monitor procedure, the first thing you do is lock the monitor here, lock the monitor. And then you do something. And now you reach a point where you need to check the condition. So if the condition is not met, you wait. You wait on this condition variable and relinquish the monitor lock. So when you are back, that is, you are released from here, then better go back and check to see whether the condition is there or not. And this is why we use a while statement rather than if. In a horn monitor, the use of if is good enough. But for efficiency purposes, Java and Pthread choose to use Mesa Monitor. The reason is we could reduce the number of context switches. So wait here, release, come back and check to see whether the condition is there or not. They keep looping until you are back and the condition is there, then you go down and to do something else. And finally, you unlock the monitor lock. This is a monitor procedure for waiting on a condition variable. Now, let's take a look at a monitor procedure for signals. A thread calls this lock procedure to lock the monitor, and this thread does something, and eventually this procedure causes the condition to happen. Then it calls condition signal. This condition signal would cause a thread waiting here to be released, and if no thread is waiting there, this call has no effect. Keep this in mind. This one has already locked the monitor lock. So even though after executing the signal, the caller still has the lock. As a result, the released thread from here does not have the lock, becoming the owner. When this thread has a chance to reacquire the lock, this when the caller eventually unlock the monitor. But that does not mean once the caller to condition signal exits, the release one would get the mutex lock. No, not at all. Because there could, if the only one waiting to act to acquire the mutex is the release one. But typically in a complex Pthread program, it may have more than one. And this is why for a released thread, if it's unlucky, it may wait for some time before it can get back. When this unlucky thread gets back, the condition could have already been changed. So this is an example telling you how to simulate a Mesa Monitor. Now let's write a program, readers and writers. This is a very, very good example illustrating many ideas. Please refer to our monitor units and semaphore unit to learn more. So we add a condition. not the condition variable. We want to add the condition to the original readers and writer statement. We want to enforce this if a writer is waiting to write. Whether a writer is the reason for a writer to wait is because either there are reader reading or there is a writer writing. If there is a writer waiting, then readers should wait its turn. In other words, unlike the reader priority version, when a sequence of overlapping readers comes in, the writers could stop. So in this way, we make sure if a reader coming and sees there is a writer waiting, then this reader blocked itself. So we are going to write a Mesa Monitor to do that. We have a mutex m lock. This is a monitor lock. And condition variable turn is you should block everyone. Reader, waiting, writers, and so on. So we have three variables: reading, counting how many readers are reading initially 0. Writing how many writers is writing 0 or 1. And writers indicates how many writers are waiting. All three variables are initialized to 0, just like here. So we initialize a mutex lock using default value. We initialize a condition variable using all default values. And the reading, writing, and the writers are initialized to 0. Now, let's take a look at how we implement a reader. So a reader coming in, lock the monitor. Then this reader check to see, are there any writer waiting? If there are writer waiting, then I block myself on the condition variable turn and relinquish the monitor lock. So I'm blocked it. When I will be released by a signal, then I check to see, is there a writer writing? Here, I check to see whether there are writer waiting. Here, I check whether there is a writer writing. If there is a writer writing, I block myself again. So if I can pass through here, it means there is no writer writing. Of course, I can read. Therefore, at 1 to reading. Then exit the monitor. So this is the monitor acquire procedure. Then start reading. After reading, I'm going to release the database. So lock the monitor, subtract 1 from the reading reader, and then signal the turn. So signal turn could signal a thread here or here. We will analyze it later. So if there is one thread waits there, that thread will be released. If no one is waiting, then this signal has no effect. Eventually, unlock the monitor. So this looks pretty easy. Then let's look at the writer. The writer locks the monitor. This is the writer's acquire, writer release. The writer locks the monitor. At 1 to writer meaning, okay, I may have to be waiting. So keep looping here. If there are reading readers, or if there is a writing writer, I block myself. Relinquish the monitor lock. So keep looping. If I am here, it means there is no writer writing, there's no reader reading. So I can safely write. So the number of writing writer becomes 1. Then unlock the monitor. After that, I am the only one to write. Then check to see the release. So a writer release is locked in this way, lock the monitor, subtracting 1 from the writing writers and also subtracting 1 from the waiting writers. Then signal and release the lock. So think about why it's here, the waiting writer rather than somewhere else. It's obvious. I hope you can figure it out. Then let's analyze this solution. Always keep this in mind. Pthread uses Mesa type monitor. Now, this while and this while are reasonable. This while means a reader once sees there is a writing writer. So keep looping here, waiting, reasonable. And this while, this is the writer part. So I only take this here, I remove all the unnecessary part. So this is the writer part. The writer would loop as long as there are reader reading and there is a writer writing, we loop. So far, these two while has no problem at all. Then why we have an if here? As we mentioned in a discussion of Mesa Monitor, when you get released, it could change. So why we have an if here rather than a while? That requires some explanation. Now, I draw a line here. This line is very important because after a thread released from this turn dot wait, it may not be able to execute the while statement immediately. Between the release of the thread here and between the time this released thread executes while, it could take some time. During this period, some other thread could enter and exit the monitor, changing the value of writers. Hope you understand that. Therefore, before the release of thread can get to the while statement, a writer could come in and making the variable waiting writers to become non-zero. So this is important. But readers, a reader at least try to wait if it sees there are waiting writers. Okay? So a release thread execute this while loop. During that moment, the value of writers could be non-zero. In this if statement, if the writer is greater than 0, a thread must wait. But when this thread gets here, the waiting condition for this thread to wait still there. But this thread has gone through the pretended waiting and execute to access the database. So a thread waits here could be signaled by a reader here, or could be signaled by a writer here. So let's explain further. If a thread here, waits here, is released by a reader. So the released thread may not see writer greater than 0, but the released one waits for no writing writers. If there are readers reading, that is when this thread is released and there are readers reading, it's okay for this thread to go down because reader can read simultaneously. Therefore, whether there are waiting writers here doesn't matter. And then what if this released thread is released by a writer? So by the time the released thread is running, situation can change. It must wait again. When a writer signals this one, at that moment, there's no writer writing. Of course, there's no reader reading. But by the time the release thread gets to while, the situation could change dramatically. So this thread must wait until there's no writer writing. So it's still good, isn't it? Then we put everything together, a bit messy, but you simply read the explanation in a clockwise way, you know everything about this solution. And finally, I would like to ask you a few questions. First, in this solution, writers must wait until there's no reader reading and no writer writing. This is fine. On the reader's side, readers wait until there's no waiting writers. Does this solution work properly? That is, readers wait until there's no waiting writers. Does this solution work properly? In other words, does this solution successfully and correctly implement the take turn assumption on the first slide? This solution does not force the writer to wait until there's no waiting readers. Can you do that? What if the if statement is changed to a while statement? What goal or goals can be achieved? And finally, if all the while statements are changed to ifs, and this is for type monitor, what can be achieved? Is this solution still good? These are good questions for you to think about it. Then let's move on. Earlier, we discussed how to simulate the Mesa monitor. Can we simulate the whole monitor? The answer is yes, but we need general semaphores. The Pthread standard does not have semaphore, but the POSIX standard .1b has the Unix type semaphores. We did not discuss Unix semaphores, but we discussed the theoretical and the use of the Unix semaphore at the end of semaphore discussion, which is a general semaphore proposed to solve the original general smokers problem. So with POSIX.1b semaphores, it's easy to simulate a Hall type monitor. So please refer to the set of slides, slides 80 to 83, or you watch this set of videos from 12 minutes 4 seconds. Check the slides and video page here. It's all available here. It's for MTU site. And all of these videos are also available on YouTube. From the MTU site here, you should be able to access the videos on YouTube or download the video from the MTU site. Now, finally, let's conclude our last lecture with two slides. That is the use of languages versus the use of libraries. Libraries are extensions to a sequential language. For example, C doesn't have multi-thread capability, but with the help of Pthreads, you could add an extension of thread programming to C programming language. In addition to Pthread for Windows, or even for Unix, there are tons of available free or commercial library for multi-threaded programming. So in this way, programmers may try various approach that fits his or her needs. Programs can be developed without requiring any change in the tool. That is, you purchase a set of libraries, you compile your program and link your program with the library. So you don't have to buy a new compiler. Libraries may not be well-defined and completely portable. That's the problem. For example, before the advent of Pthread, there are so many threads there. If you use a C thread, then you may not be able to run your program with C thread on a system on which C thread is not available. Now, what if you are used to XYZ thread library, but now you get a new assignment? In that assignment, you must use some other thread capability. So it's not portable. Some features may be very difficult to define or implement. For an example, for type monitor. As far as I know, very few library-based thread programming system implement for type monitor. And programs may be difficult to understand because the API function calls can scatter everywhere and sometimes cryptic. Now, you see the Pthread, of course, you could redefine each Pthread name, but anyway, it's going to be kind of difficult to understand. That's for the language, for the libraries part. Now, how about language? If the thread capability is language-based, for example, Ada, Java, C#, and the new standard of C++, the intention of the programmer is easier to express and easy to understand by other programmers and by program analysis tools, because the thread capability is already part of the language, well-defined and rigorously defined. But languages usually require the standardization of new construct and perhaps new keywords. For example, a language standard may have a new standard every decade, sometimes maybe even longer. For an example, Fortran 1 was standardized in 1966. Fortran 4 would be 1977. And Fortran 90 is many years ago, many years later, and so on. So it takes time to standardize a language and understand what new things can be put into the language without contradicting the original language. The semantic has to be thought very, very carefully and clearly so that no conflict with each other. And a language would add new keywords. But adding new keyword into a new standard is risky. For an example, suppose you introduce a keyword, just thread. But what if my old program has already used thread as a variable? That when I compile my old program under the new standard, the new standard compiler would complain about you cannot use thread as a variable because it's a reserved word. That is going to be a headache. In a language, language features are fixed from standard to standard. Each language may only support one or a few concurrent programming models. For an example, Ada supported message passing. So you have to model all the concurrent need based on message passing. Java has so many concurrencies and synchronization features though, but it's so scattered around. Many people complain about its monitor implementation, it's so weird. So once you have something weird there, it's very difficult to change because people are have been used to it. So each language may only support one or a few concurrent programming models. It may not be very flexible. So it's your choice whether you're going to use a language that supports concurrency and synchronization or a library. It's not only a personal preference. You have to also consider the environment you are working with. For example, is your environment has a Ada compiler available? If not, then Ada is gone. And if your environment supports Pthread, even though you are used to it, but if your environment does not support Pthread, so Pthread is gone. So you have to consider these pros and cons very carefully before choosing a tool. In early 1980s, I started my career in concurrent programming. The first choice was PR1. But sooner or later, I found out PR1 is not powerful. Then I have to go into assembly language. And then we have Unix, we have fork, and so on. Then Modular 2, Modular 3 appeared, and some education or research programming language like Concurrent Euclid, Turing Plus, and other educational language like Pascal FC. It's all appeared in the 90s and 80s. That helped a lot. But today, many language has already had this concurrent programming model built in. It's your choice. It is your choice. So if it's possible, there are close to 40 lectures. Go through it, you'll learn processes, creation, synchronization, thread, and all sort of needed basic skills. I hope at this last minute, my lectures will help you learn concurrent computing more and more effectively and easier. Thank you very much. This is the end of my concurrent programming lecture. So if you have questions, don't hesitate to send me email. Thread Manager is available at the MTU site. So you could download the binary for Linux 64 bits and install it on your machine. You could build a virtual machine if you don't have Linux, and that system is built on top of Red Hat. If you do not have Red Hat, well, you could use a virtual machine and download Red Hat for free. So at this moment, I wish everyone following my lecture would have a very, very successful career in concurrent programming and in general programming. Goodbye and good luck.